G'day, I'm Ray Tomes from New Zealand. I'd like to welcome you to this Scientific Cycles seminar. It's the first one we've had in a very long time, but hopefully there'll be many more to come. I'm going to introduce you to a number of different speakers as we go along. But first of all, I'd like to just go through a little bit of the information about the background to how this came about. So you're welcome. This is the first Scientific Cycles seminar in a long time. It seems that even cycles seminars run in cycles. I'm Ray Tomes, the Director of Cycles Research Institute and the Science Director of the Foundation for the Study of Cycles. I want to give you some background to the Foundation for the Study of Cycles. It was started in 1941. Edward R. Dewey, who had been an economist, starting his career right after the 1929 share crash had happened. And he was a very good student of economics, and he was employed by the government, and he was given the job by the president to say why had this crash happened. And so he went out and he asked 100 different economists what they thought, and he got 100 different answers. And he said the only one that he thought was right was the one that said to him, "Edward, we really don't know," which of course has to be the correct answer, because otherwise they would have done something to prevent it. Anyway, he was working on cycles for some time, and in 1931, there was a cycles conference held at Matamac, which is in Canada, of a lot of people from all over North America to study natural cycles. And they'd found some very interesting stuff. For example, lots of different animals had a 9.6-year cycle in their populations, and there were other groups that had a 4-year cycle and different other ones that they found. And when he discovered this information in 1941, he immediately got in touch with the organizer of that conference. And within a very short time, the Foundation for the Study of Cycles was started. So it was actually a combination of studying cycles in markets and business and in nature and science that led to the start of the Foundation for the Study of Cycles. They published a magazine and journal for many years, and it was a main centre for cycles in the Western world. I joined the foundation in the late 1980s, and I was an international board member, speaking at a number of conferences in the following years. In the 1990s, the foundation had some problems and went defunct in 1998. With some other past members, we decided to start a new internet-only cycles organisation, and we called it Cycles Research Institute. A few years later, FSC reappeared, and we tried to work with them, but it was not to be. Although they did some great work, it was done at the time. There were also issues with the foundation, and it failed again. Then a couple of years ago, a letter from Richard Smith was posted to a new Foundation for the Study of Cycles, and it was very clear that it was being organised on a proper basis. Very soon after that, the Foundation for the Study of Cycles and CRI agreed to combine their efforts, and I was appointed as Science Director for the Foundation for the Study of Cycles. Other CRI advisors became advisors to the Foundation on scientific subjects, and a number of those will be giving talks here, plus some other people during this seminar. So I'd like to especially thank Richard for the good work he did in getting it re-established, the foundation, and doing it on a proper basis, a proper charitable basis, and a proper democratic basis that it was being set up on again. That's very important. Now I'm going to introduce the first speaker, which is me. And I'm going to talk about the 586 million year cycle in geology and climate. One moment. I'm supposed to first of all tell you a bit about me. I'm going to do this in the third person. While working in systems software development and economic modelling for prediction, Ray Tomes discovered the importance of cycles and joined the foundation in the 1980s. He spoke at numerous FSC conferences and ran a unit trust operating in futures markets. While studying cycles full-time, he developed the harmonics theory to explain the observed pattern of cycles in the entire structure of the universe. He founded Cycles Research Institute, developed Cycles analysis software, and speaks internationally. He has joined the Foundation for the Study of Cycles board as Science Director. Tomes is based in New Zealand. That's why I said good day, so you know that. The speakers today will be coming from around the world, Australia, New Zealand, a number in America and one in Europe. So we are an international organisation. So my talk today is about the 586 million year cycle in geology and climate. Professor Afanasiev of Moscow University determined very accurately the period of geological cycles using his nanocycles method based on the changing period of the lunar orbital parameters. His 586.24 million year period and fractions of this are seen in the climate records. That's the short version. I first became aware of all of this when I came across a book called Megacycles. This is a picture of the book, and I came across it in the Auckland University Library. It was published in 1981, and the editor was George Williams, who's an Australian geologist. It was a result of a conference on geological cycles that talked about the many different cycles that they had found. At the time, I took a note that they had found cycles with ratios of 2 to 1, 2400, 1200, 600, 300, 150, 74, and 37 million years in period. The geologists clearly linked the cycles by these ratios of 2. This is a thing which I was familiar with already because I observed it myself, and as soon as I found out about their foundation, I discovered that Edward Dewey had also noticed that there were lots of cycles at ratios of 2 and sometimes at ratios of 3. I also realized that there were some other ratios occasionally between different common cycles. This is a list of some of the cycles that were reported in that book, Megacycles. And you can see the periods are not known particularly accurately in many cases, but going upwards from about 600 million, there's about a 1200 and 2500, so doubling. And coming down, we find some examples of 300, around 150, then 74, and the other one, which was mentioned, is 37. So I realized that the 74 and the 37 were measured more accurately. And if we doubled up from those, we realized it should be a bit less than 600 million years that cycles period was. This is an example in climate of what has happened to the temperature of the Earth over the last 542 million years. And you can see the black solid line is waving up and down, and that does 4 cycles in a little less than 600 million years. So that's a little less than a 150 million year cycle. At the dips of that cycle, at the bottom, you can see the blue patches are what they call glacial periods. And these are the times when the Earth has ice ages. In the last 50 million years, we've been in what's called an ice age. At the moment, we're in what is called an interglacial. So that's a period where the temperature briefly pops up a bit as it is at the moment. And those periods are usually only last for 10,000 years or less, and we've already gone more than that. So by some accounts, we are due to go into the next ice age. However, on other versions of this graph, we'll see that we may actually be past the bottom of that, and we may be about to finish the interglacial and begin the slow rise up to the hothouse world again. And that may be what we're already seeing. Now, that black line there does 4 cycles in that period, so it's actually a quarter of 586 million years. One of those periods found there, probably, in my estimation, 146.5 million years. The blue line shows the shorter term, it shows a cycle of about 36.6 million years oscillation there, which those temperatures vary by a very substantial amount. You can see the temperature in degrees there. So we're talking about from where we are now at the peaks of that being 5 degrees centigrade higher than the world is now. The people that talk about worry about the temperature of the Earth are talking about 1 degree changes. So over these very long periods of time, there have been substantial changes, and it should be understood that during that whole period there is the period when complicated life developed on Earth. Before that, there were only single-celled organisms. In this period, all the complicated life developed, and mammals and so on all happened during this period when it went very hot. So that puts some perspective on climate change. Another book that I came across, well, I was given, I went to a conference in Russia in the mid-1990s. It was actually the centennial celebration for Alexander Chizhevsky. And along with Edward Dewey, they're the two most substantial cycles researchers that covered the whole field of things and established the whole study of cycles as a thing in its own right. After I gave my talk there about the harmonics theory at the cycles, I should mention there were 500 people at this conference, and I was the keynote speaker. And at the end of it, Professor of Geology from Moscow University, S. Afanasiev, approached me, shook my hand vigorously, and handed me a copy of his book, Nanocycles Method. That title is translated from the Russian in which the book is written. I can't read Russian, and Professor Afanasiev can't speak English, but my talk was translated, and someone told me it was very well translated by the lady that did that. Afanasiev had found patterns of cycles ranging from billions of years down to years. And it was clear to me when I looked in his book, just flicking through with the numbers and so on, that he was very pleased because I had given a theoretical reason to explain the pattern of cycles that he had found. What the nanocycles method means is, I think we need to go to me for a little while here. Okay, I'm going to wave my hands about a bit here. Imagine this is the orbit of the Earth around the sun. We're going around like this. People know that the axis of the Earth is tilted 23 degrees. So as we go around, we get summer and winter at the different sides of the Earth. The moon's orbit is tilted, and the moon tends to follow the equator of the Earth, but not quite perfectly. So it does a little wobble like this, about 5 degrees. So the latitude the moon goes to relative to the Earth varies from 18 to 28 degrees. This is very important because the moon is responsible for largely for the tides, and the sun has also an effect on the tides. And these tides are not only in the sea, they're also in the atmosphere. So there are quite substantial effects by the different latitudes that the moon goes to, and that latitude affects things. Now, one of the important things is where the orbits cross. So we've got the orbit of the Earth here and the orbit of the moon here. This thing here where they cross is called the node of the orbit. And that's important because at that time, the sun and the moon will be in the same direction and you get stronger tides. You can also get eclipses at those times. Someone's asked a question, where will we find information on harmonics and multipliers and divisors? I'll post a link to that at the end of my talk. So this is the part in the book where Professor Afanasiev does the calculations of the moon's orbit. Now, we're not going to follow this in the Russian, but I'll just point out on the left-hand side, you'll see some very precise numbers. There's a formula there, and some of those numbers like C equals 0.47450709715, that is the motion of the one aspect of the moon's orbit in years, how much per year. But these values are changing over time because the moon is gradually getting further away from the Earth from the tidal action. These parameters are changing, and this is what makes this nanocycles method possible. So at the present time, this table is running 0.0 on the left-hand side there is the present time. And then we go back to 0.2 million years ago, 0.4, 0.6, 0.8. And the book runs on like this to over 600 million years ago. The first number after that, 9.298, is the time between the node of the moon's orbit crossing the plane of the Earth's orbit. So at the moment, it takes about 9.3 years. It's commonly talked about as that. The full cycle is 18.6 years to return to the same place, but there's two nodes, so we get it in 9.3 years. Now, that's not the end of the story. If we could measure that cycle, it would give us some idea because it's changing gradually. But there are secondary cycles because there's often a rainy season in any one place. The timing of that is important. And for example, in several places in the world, it's observed a 31-year cycle. This is seen in Africa. It also shows up in the prices or the production of rice in China, a 31-year cycle. And that comes about because after the node, when the node comes once, it comes back again in 9.3 years, then in 18.6 years, then in 27.9 years. And at that point, it's only 0.1 of a year away from being at the same time of the year. And that is important at the time of the year because often each place has a rainy season or not. So the 31-year is the actual average of that, the average interval after which the node will come back to the same place. There's a secondary effect, which it will get more accurately again over these other periods, 87.58 years, 108.6 years, and so on. And you can see that these numbers change much more rapidly than the initial cycle. So by measuring multiple cycles at any one place, and getting those accurately, you can determine very accurately by interpolation between these other figures, what is the age of a deposit that's being studied. Now, a lot of this was worked out from the salt deposits in Siberia, where they're laid down each year. And these yearly deposits are called varves, and they happen wherever water is carried down to a lake or a sea from rivers. These deposits are put down, and what will happen each year is when a bit of dust and stuff, dirt, is carried down by the river, the larger particles will settle out first. So you get those, and then as the time goes by, the smaller particles settle out. Then the next year's one come, and you get it. So you get this alternating of larger and smaller ones. And these can be very, very fine deposits. They may be fractions of a millimeter even that are measured. And their microcycles can be observed by going through those. The other cycles can be found where there's bigger deposits and smaller ones and so on over a longer period of time. So this is just 2 pages of Afanasyev's book, and it goes on many pages there to show that whole thing. So a geologist can look this up, the cycles found in the varves, and determine what is the age of the deposit. Now, this method is now well known in Russia, and it's fully accepted there. When I tried to put this information into Wikipedia, I had various geologists telling me, no, you don't know what you're talking about. There's no such method. And they deleted it from Wikipedia. So sometime soon, we're going to make a concerted effort to get it back into Wikipedia. I'd like to get Afanasyev's book translated into English so that the whole thing is available in English. So these are things that we can still work on with the Cycles Foundation. This is I should have shown that bit before. That's showing the figures a bit larger that you can see that right now we get a 9.298 year cycle, a 31.21 year cycle, and so on. And 0.2 million years ago, that was 9.268 and 34.66. So if we found something like about a 9.29 year cycle and a 32.5 year cycle in the deposit, we could look where that is and say, oh yes, that's 0.08 million years ago, or 80,000, and we could work all of those out. Yeah, the age of the deposit. This is from Professor Afanassiev's book, and it was when I saw this page that I understood why he was interested in my talk. It runs from 1 year on the left through to 5 or 10, about 10 billion years on the right. And it shows the length of different cycles that have been found in the many, many, many determinations they've made of cycles. You'll see the big peak. If you can see down there, the bottom right, there's a figure 500, about a fifth or so of the way across, and there's a bigger peak there. That peak is at 586 million years, and that cycle has been determined more accurately than any other cycle. The figure that he got was 586.2385 million years, and that's accurate to probably the last place. That compares to the Western geologists who said it's about 600 million years. And it's this method that enabled him to do that so accurately. So it's a very important discovery that he made on how to do this. An example of applying this the cycle, it's interesting because this story involves George Williams and Professor Afanassiev again. And George Williams had given this information that there was a cycle called in the Alatina deposits in Australia. And it was dated to be about 650 to 700 million years ago. And it showed a very clear 12.077 year cycle. But that cycle was modulated by 314 and 157 years. So the cycles got larger and smaller over that period. The cycles also were alternating in strength, which was an important clue. There was debate in the literature, in the scientific journals, about whether this was an ancient record of the sunspot cycle, which was what George Williams said, is this a sunspot cycle from 600 something million years ago? Or whether it was perhaps could have been caused by a lunar cycle, and maybe these were the months of the year that were happening then. The third possibility, which is what I'm suggesting here, is that these are just the cycles described by Professor Afanassiev, and that very accurate dating is possible. Using the nanocycles method, the Alatina formations are dated to 658.28 million years ago. So rather than saying 650 to 700, we can give it to that high accuracy. Confirmation of this is very strong because the nanocycles identification is correct, because a 12.077 year period is expected to have a further period of 12.077 divided by 0.077, which is 157 years, exactly matching one of the reported longer cycles. So from that, we can say very confidently that the cause of this cycle is the changing movement of the lunar node, and that it does date from 658.28 million years ago. So what's been done here by Professor Afanassiev and other Russian scientists played a part is to have this very accurate method of dating things and to understand what is going on with all these little cycles in the long records of geological deposits. So whenever the geological deposits are seen, and you will have seen this yourself, that we find a cliff somewhere that's been fallen away by the weathering, and you can see all these different layers up the cliff. And amongst those, one moment. Sorry, just changing my screen sharing so you can see me. At least I hope I am. Nope, I haven't done it right. Let's try again. Lars, can you tell me, are you seeing me now or what? Okay, great. Okay, thanks. I'm a little bit of an amateur at this, doing this. So the result of this is it's very, very important for geology that Western geologists learn about this method. When we look at these cliffs, and there's some beautiful ones I found near where I live, and I would like to talk about those some other time. There's some other very interesting stuff in what's left when they're washed away. But we'll see these layers, and you'll often see dark patches and another dark patch and so on going up the cliff, and they run all along the cliff. It's quite clear that what was happening on a wide area. But if we go closer, we'll find some smaller, darker and lighter patches, grainier ones and smoother ones. And when these are analysed, there's often different chemicals and all sorts in them. So these these big cycles have been studied, and are part of the reason why we know about these very long cycles. But people hadn't studied in the West these very tiny cycles that can be found, which are only millimeters or fractions. So what has to be happened is you have to magnify the whole thing and then count off how many years of that has happened and what's happening there with those cycles. And that's what George Williams did in these ancient deposits to find these 12.077 year cycle and so on. So that's the method that has been developed by Professor Afanasiev, and which, if geologists would see this and would start to research into this, we could be using in the West as well to date things more accurately. Now, I want to put in perspective there these long cycles. We know that there's this 586 million year cycle, and there's other ones with a half of that and a quarter and an eighth and a 16th and so on, and also probably double it and quadruple it, but those ones are harder to detect because they're such long periods. But when we come down to shorter periods, so that one causes these huge swings between the ice ages and the hothouse times of the Earth. When we come down to shorter cycles, there's the ones known as the Velenkovic cycles. So we have climate changing quite substantially. At the moment, we're in what's called an interglacial. So it's a short period where the whole world isn't covered in ice. And the time between the ice ages, the cycle is about 100,000 years. The Velenkovic cycles has 4 cycles, 100,000 years, 40,000 years, and 23,000 years. And these interact, so you get a wobbly curve, but every so often we go up to a big peak and come down again. At the moment, we're just past the warmest part of that. We came out of the last interglacial about 10,000, 11,000 years ago. We came out of the ice age into this interglacial. And on the average, these things only last less than 10,000 years. So theoretically, we're due to go right back into the next ice age. In fact, some of the universities that are now claiming we've got a runaway hothouse effect, in the 1970s, they were publishing papers saying we're about to enter the new ice age because the Earth started to cool for a little while. So we need to understand, first of all, that they're not always making good predictions. This period in the 1970s was actually a dip in a 60-year cycle, which hit a peak about 1940 when we had the Dust Bowl in America. Before that, it was cooler again in the 1910s. We went cool in the 1970s, and then we expected to hit another peak about 2000, which it did. Now we've tended to stay up at a higher temperature since 2000. Theoretically, we should have been dipping on that 60-year cycle, but on these longer cycles, the Velenkovic ones, we would expect to be going back into the next ice age. Now, in this longer cycles, very long, the hundreds of millions of year cycles, remember you get so many of that short cycle and the long one. It's a very different perspective. You know, we're zooming right in and zooming right out to see these things. On that one, I believe we're already past the bottom of the ice age cycle, which is the 146 million year cycle, and that we're already on the way up. Now, as that goes up, the ice ages will stop happening and we'll be heading gradually towards, it'll take another, 70 million years to reach the next hothouse of the Earth. The hothouse of the Earth will have a temperature maybe as much as 10 degrees warmer than it is now. So the variations that we're seeing from year to year now are nothing compared to what has happened on the Earth in the past and what will happen in the future. Of course, one of the concerns is that that's happening too fast, and that's a valid concern. But the idea that life is going to all cease to exist if we go up a couple of degrees, that's a nonsense. Life has existed through much higher temperatures than now, and it's not going to kill all the polar bears, it's not going to wipe out other things. The thing that's causing those to disappear is humans destroying habitats all over the world. So that's my little rave on a side subject. Okay. Right. I'd like to give this a little mention. Someone's asked about the harmonics and multipliers and divisors. This is a little sidetrack into the talk I gave in Russia on the harmonics theory. Now, I'm not going to try and give you the whole harmonics theory here, but it basically says that the universe is oscillating and that each cycle, because of non-linearities in the laws of nature, develops smaller cycles that are exact fractions of that. Now, it was, first of all, I developed this from a study of cycles in the range from sort of like days through to hundreds of years. But gradually, as I studied further and further, I found there were longer and longer cycles that fitted the pattern. And eventually I realized this was actually an explanation for how the whole universe operated. Now, I got the different cycles periods that I knew, and I analyzed them according to what was predicted by the harmonics theory. And when I did that, it was able to identify the ratios all the way from up to the 600 million year cycle period, right down to about a month, and find the exact ratios that were between these. And if we start from the 586.24 million year cycle, it does go half of that, half of that, half of that. We can see those cycles quite accurately. But then what happens is there's a ratio of 11. Now, the harmonics theory predicts that this will happen, that from time to time, there'll be lots of ratios of 2, a number of ratios of 3, but occasionally there'll be a 5 or a 7 or 11 or a 13. And it turns out that the 11 happens right up there. Now, I didn't expect it to happen to much further down. And the reason is that the universe is much, much older than what the Big Bang theory people think. That the longest cycle of the universe is 10 million times longer than the age of the universe, according to the Big Bang people. Now, I'll give a talk another day to try and get that for you. I'm just trying to answer here the question about these harmonic multipliers and divisors. And that ratio of 11 occurs, and that produces a cycle of 26.64 million years, which is the cycle of extinction events. Now, not all extinction events fit that one cycle, but a majority of the big ones do. However, the last one of those was millions of years ago, and we're not due for another one, but we are actually having an extinction event at the moment because of human activity. So that one, we can then divide that one some more, and we divide it by a couple of 2s and a 3 again. We get to 2.22 million years. This one shows up in the dynamics of the solar system, the interaction of the planets, and the changing of the orbits of the planets, and 1.11 does as well. And that one, and that particular one, energy is exchanged between Jupiter and Neptune so that their orbits get come a little bit one way, a little bit the other way. Neptune is the main one that gets pushed about because Jupiter is so much more massive. And we can follow that on down, and we'll get to 4,600 years and 2,300 years, which are well-recognized climate cycles. And they are also cycles in the alignments of the outer planets. So at those intervals, the outer planets make especially good alignments. And that has been a number of people in the field of climatology have recognized this and have felt that this must be an important reason for why the climate changes, that is to do with how the planets influence the sun. And there are a number of theories on that. And of course, I've got one as well. And they, but it's generally agreed that something's going on there with those longer cycles. And we come down further, we get 178-year cycle about. And during this part, we get a ratio of 13, which is from the 2,300 year down to the 178 year. From there on, we get ratios of 2 and 3 and one ratio of 5 to get into the range of common cycles that were reported by Dewey, which included, he started from 17.75 years and he went up and down there by ratios of 2, but also by ratios of 3. And those cycles are all visible. Now, I do have if you search on my name and the main line of harmonics, you will find a table showing all of these cycles, which I'm not putting up here at the moment. That will give you accurate figures for all the common cycles. And for example, although Dewey knew that there were these ratios of 2 and 3, and although he clearly had some cycles that were a ratio of 5 different, for example, he had a 2.22 year cycle, and he knew there was an 11.1 year cycle in the sun, he didn't mention that's a ratio of 5 different. And I guess he didn't want to complicate what he had there, but at that ratio of 5, larger than the common cycles he had, there are another set of cycles, solar cycles mainly, and if we divide them by 7, there's another set of cycles, much shorter ones in the days range, which include some short solar cycles, like there's 154.7 day cycle in the sun. And these ones all fitted that pattern that I calculated from the cycles that were known, and the harmonics theory gave these figures. But it also came out with a 9.638 year cycle. And it's interesting because Dewey had found a 9.6 year cycle. And when I looked at all the figures he had two sets of figures, which were 9.6 and 9 2/3 years, which is 9.67. And the average of them was 9.63 something, agreeing extremely well with the figure that I got. And before that, it was not known that this does in fact fit the ratios of these that were there as well. So that fits in the whole scheme. And the most common cycle of all, according to Dewey, as in terms of reports, was called the 40.68 month cycle. Well, it was called the 40-month cycle, but he determined it to 40.68 months, which is 3.39 years. And that cycle can be found from his common cycles. If we divide one of them by 7, we actually get that figure. And that one, when we halve it and halve it and halve it again, we get all these common cycles in the sun, 154.7 days and fractions of that. So all of this picture becomes clearer when we start looking at the harmonics and ratios of these things. And the figures that we get are very accurate. So when someone's doing cycles analysis and they find a cycle that, for argument's sake, 11.9 years, we can say, well, that looks like it's the 11.86 year cycle of Jupiter's period around the sun, which is one of these very common cycles that shows up in this whole structure. So if you're doing cycles analysis, identifying a cycle accurately enough to determine what's the actual underlying cycle, you can use that period for your predictions, and that will be more accurate. So that's a useful thing. Okay, I wonder if there's any more questions, Mark. No? Okay. Oh. Someone's asked, are you aware of any studies of financial market turning points and moon phase cycles nodes? The most of the ones that we have for the node cycle for the moon and the phase are natural cycles. And one of our later speakers will in fact be talking about that, about disasters happening based on the nodal cycle. There was a guy, Louis Thompson, at the foundation who did many studies about the 18.6-year nodal cycle and the agriculture. But offhand, I can't think of any in the financial market that are following that period. No. Dewey lists common cycles, and that's 18.6 is one of the common ones. But that, as far as I can remember, that doesn't have those have the financial markets, and that doesn't to say there aren't some, because there's so many measures. Okay, well, that's about it for me, thanks. Oh, hang on. Yeah, okay, someone else has asked, life won't cease to exist, but it could cause havoc for humanity and other species. Yes, so this is referring, I think, to the changing temperature on the Earth. It depends how fast it changes. There's always havoc. Climate is always changing, and there are always events that cause massive things to happen. So like at these 27 million year cycles, it doesn't just cause havoc, it actually causes the extinction of tens of thousands of species at those times. To kill it, get an extinction of a species, you have to kill 100.0% of the members of that group. So yes, we can say for sure there will be future disasters, there will be future climate changes that are disastrous, and some animals will go extinct, and it will cause havoc for humans. Personally, I don't think that what human causes of that, the main cause of it is temperature change or carbon dioxide. It's a small factor at best. The biggest factor that we're doing that's causing problems for animal life is the destruction of habitats, the destruction of rainforests, the human expansion of population, which is starting to get under control, and wiping out large areas of forest to grow cattle, put cattle instead of trees. That has a bad effect. And someone else has asked, what would it take to recreate Dewey's original cycle synchrony studies today? Yes, that can be done. One of the things that Cycles Research Institute offers is a program called CATS. It stands for Cycles Analysis and Time Series Software. That comes with some large number of series of data, and some of them are like daily data, some are monthly data, weekly data, annual data, some of them are decade data, and so on. And with CATS, you can analyze each of those and find the turning points, the periods of cycles in it, and the turning points of them. So when you do that, you can build up a big database of those. Now, I have done this, and you can find things that go together. So, for example, there's records in there. There's monthly data on a large number of commodities in Europe for many hundreds of years. People have done studies and gathered this data like from the 1300s through to the 1800s. So with those, and you can see that all the different grains move together. There are differences, but there's common times when all of them come to peaks together. So that can be done. We should be building up a public record of those. We should have many people working on it. We should have people adding more data to this database. And in fact, behind the scenes here, Lars is operating things so that we have the conference operating here well. And he's a very good technical man on this. And I want to talk to him about putting CATS available online. At the moment, it runs on a PC, but it would be nice if people could use it from their phones as well. It'd be nice if we had a system where people can put data in, and do analysis on them from their phone. Now, this is a development project we should do, and this is an appropriate point for me to say, you can join the Foundation for the Study of Cycles and participate in these things. It's very cheap to join, it's $99 a year. And one of the things we'll do is we'll be making extra things available to those people, but it helps support these projects, and you can join in and help these projects. So we're seeing a blossoming of the foundation at the moment. And so that's, it's a very exciting time, like when Dewey first started it. And it's the coming together of scientific cycles and market cycles. The truth is that the scientific cycles people will make some more discoveries, but we need the market cycles people because they're the ones that make the money. And when they come together, we get this wonderful blossoming effect, and we are starting to see it happening again now. Yes, someone's asked, is there a good book to read on harmonics and cycles? Search for Edward Dewey. What's it called? The Case for Cycles. Search for The Case for Cycles, Edward Dewey. And this is an article that was published. It's not a full book, but there's quite a few pages. And this is a very good place to start to give you an overview of all the things that were discovered in cycles during Edward Dewey's time. This article was written in 1967, but it's still extremely good to give a background of the whole thing. And for example, using some of Edward Dewey's data on the phase of the different cycles in the stock market, in 1986, I predicted that there would be a crash in 1987 in the stock market, which there was. I was a month out, but that was near enough. But it wasn't until a couple of years later that I visited the Cycles Foundation and I found Dewey's work, and he had work done in the 1960s on stock market cycles. And when I ran them forward, they also predicted the 1987 crash. So 20 years ahead, he could predict those because he had worked out the cycles very accurately. If you want to find me, look on Cycles Research Institute, Ray Tomes, or you can go look for my personal website, Ray Tomes, and you will find information there. I can put here for those that the best way, comments put on YouTube is a good way to contact me, because I will be looking at the comments on YouTube for this talk and for other talks to go. And there are more further good books to read, but I would highly recommend starting with Edward Dewey, The Case for Cycles. It explains to you about the cycle synchronies, about the ratios between the different cycles, and it gives you a good feel for all the different fields in which cycles we found. Thank you. Richard has just welcomed me to the Foundation for the Study of Cycles, and it's wonderful to have someone like Richard in charge of the organisation, and he's selected a good team together, some old people from the Foundation from before and some new, and they've employed Mark McVeigh, who's operating, making sure everything's happening and gives everyone a push along when they need it and helps them to get the things happening. And Lars in the background here, and all the other team of the directors of the Foundation. It's a wonderful team, and I'm looking forward to an exciting future. That's it for me. Thanks. Yeah. Okay, so Lars has just informed me. I'll just have a little chat now, and then this will be the end of my talk. And the next one will start in about 10 minutes from now. So I'll prattle on a bit more. Yes, someone else has asked a question. Would Hurst be another one who predicted all the different cycles? Yes, Hurst found a whole series of cycles. He had a slight. It's worth mentioning that when I first did my work on cycles, I had a period of 35.6 years, and I found that a lot of the common cycles were fractions of that. So if you take half of that, you get 17.8 years. Dewey had 17.75 years. So it agreed quite well, and he had a lot of the same cycles that I had. He had more than I had because he had studied a lot more different series than I had. But interestingly, people were telling me it was just a fluke, but interestingly, Dewey's data came from an earlier period than mine, from a different country, and many different subjects, and exactly the same pattern of cycles was found in them. Hurst was using just the stock market, but he found a similar pattern. He had a slightly shorter period than Dewey, but again, he had lots of ratios of 2 and some ratios of 3 in his cycles. And he did a lot of work on how to predict the cycles in the stock market. One of the interesting things is cycles aren't always an exact fixed period. Often the period goes up a little bit and down a little bit, and up a little bit and down a little bit. I gave a talk in the 1990s early, when it was compulsory when you were doing that talk to give a prediction for the stock market. Well, it wasn't really, but that's my little joke. And the ones, everyone recognised that we were just passing through the minimum of the stock market at that time. And most of them predicted the next peak to be 20 months from there. But because I had found this gradual changing in the period of the 40-month cycle, I was able to predict that the next cycle will be about 6 months after that, and that was in fact correct. So as well as studying the cycles, you need to study the modulations of the cycles. It's very complicated, folks. If you just do the cycle, you'll get an answer. If you do the modulations, you'll get a better answer. That's a subject for another talk. Mark's telling me lots of people are thanking me for an excellent presentation. I hope it didn't go too fast and too many complicated things. It's something we can expand on in the future. There will be more talks, and if people have particular questions, we can address those in the future as well. We will, in fact, be having, a few years ago, I had a guy from America, David Katzmire, who's also been very active behind the scenes. And he's giving one talk today, who came over and did a lot of videos of me, and we've finally got a lot of those ready. And one of the things that we can do is once a week, there's going to be regular TV for Foundation Study of Cycles on internet, is we can release one of those a week for the next year. So those talks are on all subjects, from climate through stock market, all sorts of things, animal populations, anything you're interested in, commodities and various things, ranging from very short to very long cycles. Yeah, very good.